So this time we're going to look at the t-test instead of the z-test. And what makes it different? And for the most part, the t is exactly the same, but sometimes when they give you the data, they give you the data and you have to come up with some of the numbers yourself. However, most of the parts that we just talked about are the same. When you read the problem, you're looking for the alternative hypothesis first, fill in the null. When we go to do the actual t-test itself, t equals observation minus mean over standard deviation divided by the square root of n. And so because of that, it's pretty much easier. So I'm actually going to run through this one really fast so it gives us a harder one, because I want to show you guys some cool tricks on the ALEKS calculator. So if you have a harder one, give me a second and I'll get there. So it says heights were measured for a random sample of 12 plants grown while being treated with a particular nutrient. The sample mean of the sample standard deviation of those were 40 and 9 centimeters respectively. Assume the population of heights for treated plants is normally distributed with a mean mu. Based on the sample, oh, I'm missing part of my question. Oh, can it be concluded that the mean is different than 36? Okay, so what that major sentence, is it different than 36? Is it greater than 36? Is it less than 36? Wherever that keyword is, that's your alternative hypothesis. So this is going to be mu differs from 36 versus the null, mu is equal to 36. Okay. This is a t-test that we're working on. The degrees of freedom is always your sample size minus 1. So since we have 12 plants, our degrees of freedom is going to be 11. Okay, now for the test statistic, as I said, it's the exact same test statistic. We are actually going to take, in this case, t is equal to observed minus mean divided by standard deviation over the square root of n. So it is no different, and that's where people get confused. A t is a z, or at least he wants to be a z when he grows up. So when we look at this, the observed value was, well, let's go back to the question and see. We observed the 12 plants to have a mean of 40 and a standard deviation of 9. So we observed them to be 40. We want to know if it's different than 36, that's where our null hypothesis, over the standard deviation, which is 9, divided by the square root of our sample size, which is 36. So 9 divided by 6 is 1.5, so our numerator is 4 divided by 1.5, which is really what, like 8 divided by 3, which is 2.666. Okay. You can put that into a calculator if you want to check any of it. So 4 in the numerator, square root of 36 is 6, 1.5. So 2.66 is our answer. So when we look at our ALEKS, we're going to get 2.66 or 2.66667, if it will make ALEKS happier. Now, what is the p-value? Okay, be careful. The big difference between the picture we've just created and the picture we had only a moment ago, oh, I think we got lucky. But we got lucky, and I need to make this very clear. In this case, we got the believed value is that it would be 36. When we did our test, we ended up here. If this had been z, I'm pretending for 1 second. If this had been z, when you pull up the calculator, it's the probability that z is less than. And we aren't looking at less than, we're looking at greater than. So we'd have to do this first in the z-test. We'd have to do less than, which would give you the white region, and then we'd have to subtract from 1 because it's always 100%. The nice part is, unfortunately, nice because I can get out of it quicker, but you've got to be careful, is that in this case, when you look at the calculator, it's the probability t is greater than. So I got lucky that mine's greater than. Just be careful, make sure it's going in the right direction. So at probability t is greater than 2.6667 degrees of freedom. Now, the value we get is 0.01096, which is nice and small. But remember, that's only over here. And we always need, when it's a two-tailed test, we need to double it because it's equally likely that it could have been on the other side. So I need to times it by 2. And we get 0.02192. So at a 5% level of significance, that means we can be wrong up to 5% of the time. Okay, that's what an alpha is. The p-value is the exact chance you're wrong. So I could be wrong 5% of the time, but I'm only wrong 2% of the time. So when p is low, really small, smaller than alpha, then I can reject the null hypothesis and claim that there's a difference. So can I claim there's a difference? Yes. Now I'm hoping that I take, level of the test statistic is incorrect. That's not true. They don't like my math. Was 36 not the sample size? Oh, 12 was the sample size. My 36 was magical and came from nowhere. Good, let's fix all my mistakes here. Let's do it right. So our numerator is 40 minus 36, which gives us our 4, divided by our denominator is 9 over the square root of 12, not 36. I had just made my life nice in making that 36, but the reality is that I was not using the right value. All right, so it should have been 1.5396, not my magical number that I came up with. I'm sure you were yelling at your computer screen. You're like, no, that's not it. Sorry about that. So that I can actually, I'm going to store this number. I'm going to clear. The probability t is greater than, recall the number. Then I don't have to type. I just get lazy. 11 degrees of freedom is 0.0759, but we'd remember to times it by 2. So now there's a 15.19% chance I'm wrong. That's too high. In which case, no, I cannot reject the hypothesis, unfortunately. All right, so now that I have the answer right, I was hoping they would give me a harder one, but they obviously don't think I can answer that one, so maybe they won't. Yeah, they didn't. Come on, I want a harder one. Not a harder one, a different one that has a bunch of data, because that's actually where this is going to come in to be tougher. Nope. Less than 70 is my alternative. I just want to see if I can get one of these real quick. So my null is mu is greater than or equal to 70. It's a t statistic because I'm in the t section. So less than 70, as soon as I see those keywords, that makes it a less than test. 20 degrees of freedom, standard deviation of 8. All right. So 66 minus 70 gives us a numerator of 4. And our denominator is our standard deviation, which is 8 divided by the square root of 21. And that gives us negative 2.29. All right, good. Because I'm going to do my p-value. Notice when I go to do my calculator, my p-value does not give me less than. This is a left tail test. And so the hypothesis, I'm looking for the left, but this doesn't give me the left, which is okay. I just have to remember that when I get my answer here, okay, when I get my answer here, it's giving me the wrong tail. I wanted less than, and that's okay. It's just when I'm done, I take 1 minus answer. So just be not 10 minus. 1 minus answer, which gives us 0.0164, 0.0165. And yes, we can reject. Come on, I want a different one. Give me a different one. If it doesn't give me a different one in the next one, then I'm just quitting. But I do want to show you guys one thing. While I'm going through and fighting to find a different one. No. All right, sometimes it's going to give you data. And I just want to show you that when that happens, it looks like life is going to be so much more complex, but it isn't. So let me just show you. No, I don't want this one. Let me try one more time. All right. Well, oh, good, it did. Okay. When it gives you numbers, I just want you to pay close attention to this for 1 second. When it gives you the numbers, and that's what it's doing here, okay? When it gives you the numbers, all you do is click on the calculator. Okay. Then you simply highlight the numbers. So do you see, all I did was I opened the calculator, and then I highlighted the numbers, and you see that the numbers are in the calculator? Yes, we do. All right. If you highlight them and click on X bar, it gives you the mean. So you don't have to type them into Excel. You don't have to write them out. You simply highlight them. And similarly, if I highlight the numbers again and click on this letter S up here, it'll give me the standard deviation. And so when they give you the data to find the observation, the sample mean, and to find the standard deviation, all you do is you bring up the calculator and then you simply highlight the numbers and it'll put them in. All right, I wanted to show you that because it's a huge time saver once you actually see that it's there. All right, did you guys have other sections you wanted to look at?